Hello, welcome back to Algebra. The title of this lesson is called Irrational Exponents. Now, it's a complicated sounding title, but I promise you by the end of this, you'll understand exactly what an irrational exponent is, how to deal with them, and why they're important. I'm also really excited to teach this lesson because in the course of this lesson today, right now, you're going to learn the very first concepts that you learn in Calculus 1. Now, I very firmly believe that everything in math can be fully understandable by everybody. And I firmly believe in not babying people too much. So what I'm doing here is we're going to introduce and use the concepts of irrational exponents, but in the course of the lesson, you're going to understand logically why that idea, that very first idea in Calculus 1 that everyone learns, is very applicable to this. So pat yourself on the back when you're done with this lesson. You're going to understand the very, very fundamental concept of Calculus 1 that everyone learns the very first day of Calculus 1 in the course of this algebra lesson. So let's crawl before we can walk. I promise it will all be understandable. We want to talk about irrational exponents. Those are exponents that are, just for lack of a better word, weird. They cannot be written as fractions. An irrational exponent would be like 2 to the power of pi, because pi is an irrational number. It cannot be written as a fraction. Or 2 to the power of square root of 3. Square root of 3 is irrational. It cannot be written as a fraction. So how do you calculate things that have radicals or pi or other weird things in the exponent itself? How do you handle it? So before we do that, let's take a little bit of a trip down memory lane and talk about what we know. First of all, we already know how to deal with positive exponents. Positive exponents we've been dealing about for a long time. For instance, 2 to the positive 3 power is defined as 2 times 2 times 2, which is 8. So we know how to deal with positive exponents. We also have learned how to deal extensively with what you do when you have a negative exponent. So for instance, we know how to deal with it when we have 2 to the negative 4th power. What we do is we take this negative exponent and we bring it to the bottom of the fraction and make it a positive exponent. That negative means you drag it downstairs. Now, what you have down here is 1 over 16 because 2 times 2 times 2 times 2 will be 16. So we know how to deal with negative exponents. We have also talked extensively about what happens when the exponent is actually the number 0. It turns out that anything raised to the 0 power is defined mathematically just to be the number 1, and we've talked about in the past why this is the case. So if you're curious why it's that way, go back to my very first lessons on exponents, and I talk about it at a great length. And then finally, very recently, in the last lesson, we have talked about what to do when you have a rational exponent. That means you have an exponent that can be written as a fraction. So for instance, if you have 2 to the 1/3 power, this is just defined to be the cubed root of the number 2. Okay, or another example would be, a little more complicated example than this, would be what do you do if you have 4 to the 3/4 power, right? We can write this 4 to the 3/4 power a couple of different ways. We can write it as 4 raised to the 3rd power and then to the 1/4 power, because we can multiply these powers together to give us this. And then when we write it this way, then what we have is 4 to the 3rd power. We write it as the 4th root of that. But another way to write it, I'll switch colors to show you that, is instead of writing it like this, you could say that 4 to the 3/4 power can be written as 4 to the 1/4 power, and we raise that quantity to the 3rd power. See, the order here can be interchanged because when you multiply this and you multiply this, you get exactly the same thing. So if we do it this way, we have a 4 that we take the 4th root of, and then we raise that quantity to the 3rd power. So if we have a fractional exponent like this, we can raise it, let me just check myself, as 4 to the 3rd power and then the 4th root of that, or we can write it as doing the 4th root first and then raising it to the 3rd power. So we know we have to raise it to a power and then take the root. We can just do them in whatever order we want. Now this is all stuff that we have learned in the past. What do you do when you have a positive exponent? What do you do when you have a negative exponent? What if you do when you have a 0 exponent? What do you do when you have a fractional exponent? We've covered all of that. Now what we need to do is, what does this mean? What does this mean? And what am I referring to? Just as an example, what if you have 2 to the power of square root of 3? We have never covered that before. We've never talked about what do you do when the exponent itself, it cannot be written as a fraction or a negative or a positive number or 0. What do you do? Well, the punchline, I'm going to give you the punchline, and then we're going to go and do a little bit of background work to kind of show you why it's the case. The punchline is you treat these exponents as exactly with the same rules as all of the other exponents. You can add them, you can subtract them, you can multiply them. It depends on the situation you're in. We're going to do a lot of problems like that. But this radical up here should not scare you, right? You're going to use the same rules of algebra. What if you have 3 to the power of, 2 pi? Because pi is irrational. It's an exponent, it's a number, 3.14159. Pi goes on and on and on forever. It's irrational. But you treat those exponents with exactly the same rules that you treat any other exponents. Let's explore why that is the case. And in the course of learning how to calculate that and what it really means to calculate something like this, we're going to learn a tiny bit of calculus right along the way. So that's what we're going to do here. How would we calculate 2 to the power of square root of 3? All right, 2 to the power of square root of 3 really is the following thing. Now, I know we're not all human calculators, but basically the square root of 3 is, when you truncate it, is 1.732 ... That means these decimals go on and on and on. They never repeat, and they're not, because they don't repeat, you can't write it as a fraction. That's what it means to be irrational. So how do you calculate an exponent that has an infinite set of decimals that go on and on and on and on like that? Well, you have to use a concept from calculus that's it ties very much into what we're doing here, so we're going to kind of go over that here. What you do is you forget about all the decimal places way over here. What you do is you say, I want to approximate this. Let's approximate, since it's 1.7, roughly speaking, then let's first approximation, let's just say it's to the first power. That's a really bad approximation of this actual number. But if you would take it to the first power, you would just get an exact number of 2. All right, let's make a slightly better approximation. Let's say it's 2 to the power of 1.7. That is a little bit closer to the actual value of the square root of 3, but it's obviously not quite right because these decimals go on and on forever. But this 1.7, how do you evaluate a decimal like that? Well, see, any decimal that doesn't go on and on forever, like this one, I can write it as a fraction. I can say this is 17 over 10. I want you to convince yourself that 17 over 10 is exactly the same thing as 1.7, because when you divide by 10, you take the decimal and move it one spot to the left. So 1.7 is exactly 17/10. And you now know how to evaluate exponents with fractions. It's really gnarly, but you can do it. This is 2 raised to the 17th power. Take the result of that and you take the 10th root of it. Or you could say 2, take the 10th root of it, and then raise the result to the 17th power. So you can calculate this exactly. And if you did that, you would get 3.2490. So this number is a little bit closer to the actual square root of 3, and as a result, this number that you get is a little bit closer than our first approximation, which is really bad, because this was really not close at all, but it was where we started from, okay? All right, let's switch colors, and let's get a little bit closer. Let's get a little closer to the square root of 3, 2.1.73. We took one more of the decimals here. How would we calculate this? It would be 2 to the 173 divided by 100. Now this is again a gnarly, very ugly fractional exponent, but again, 2 to the 173 power. You can calculate that, get the result, and you could take the 100th root of it. You can do that. You could do a giant factor tree, look for a set of 100, commonality. You can get the exact number, but when you run it through a calculator, the number that you're going to get is 3.3173. You see what's happening? Our first approximation was very crude, but as we get a little closer, we get a little closer to the real value. As we get slightly more closer, we get even a little bit closer to the value. Let's get one more time. Let's go one more time and get a little closer to that, 1.732. We take one more decimal. Of course, there's more decimals after it, but this is going to be, how would we calculate it? 2 to the power of 1732 divided by 1,000. Because you divide by 1,000, you move the decimal 3 places. 1, 2, 3. That's exactly what it is. So 2 raised to the power of 1,732. That's crazy. Take the value, and then you take the 1,000th root of it. A computer can do that. I'm not going to do that. What you're going to get is the value exactly 3.3219. So the whole point of this exercise is to show you. People say, how do you calculate an exponent that has a radical in it like that that's irrational because the decimals never end? The truth is, you can't calculate it exactly, right? Because the decimals never really end. But what you can do is you can get closer and closer and closer and closer by taking more and more and more of the decimals and drawing in a closer approximation to the number. And you can see that my answer is getting closer and closer to a real value. Notice this is 3.32 and some change. This is 3.3 and some change. This is 0.3.3 and some change. It's getting closer and closer to a final value. 3.3 something something. It's going to be the actual value of 2 to the power of square root of 3. So if I continue this process, then ultimately I want to calculate 2 to the power of square root of 3. And I'm getting closer and closer and closer. This is the exact number I want. And when you run this through a calculator or a computer, the actual number you're going to get is 3.321997 ... The reason the dots is because this is an irrational exponent. It has infinite decimal places in the exponent, but I could, of course, take more and more and more decimals, and I would get an approximation closer and closer and closer to the answer you get from a computer, which would be something like this. You see the approximations getting closer and closer. So what you can do, and this is the part where the calculus comes into it here, you can define. Notice this is, we took a successive approximations, 2 to the first, 2 to the 1.7, 2 to the 1.73, 2 to the 1.732, 2 to the, this is the exact thing we're trying to find. You can define something called 2 to the power of x. Notice by putting a variable in the exponent, I can actually change the value of the exponent, just like I did here, getting closer and closer and closer. I'm just changing the exponent here. By putting the variable in the exponent, it allows me to change it to whatever I want because it's a variable up there. Okay, this thing, 2 to the value of x, is called an exponential function. Now, in just a little bit, we are going to study exponential functions in great detail. It's one of the most important functions in all of math, and there's tons of reasons I can give you for that, to tell you that so you believe me. But I'm not going to do that now. Right now, we're just focusing on understanding this rational exponent. But just know, this thing is called an exponential function. We're going to learn all about it, right? Now, if you let x approach the value of the square root of 3, that means it gets closer and closer and closer, just like I did here. Closer, 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 closer. I can't really ever get here because it's infinite decimal places, but I can get closer and closer and closer. If I let it get closer and closer and closer, I'll just write over here, closer and closer. I mean, I can continue writing decimals to the end of the universe, but I'm still never going to quite get there, but I'll get infinitely close to this guy. Then what you can write down is the following very, very important thing. You can take what we call the limit as x approaches the number, the square root of 3, but it never quite really gets there, but it gets really close. And I'm going to take the limit of the function 2 to the power of x. That means I put an x value in, a really crude one, of 1. And then I put an x value in a little bit closer, 1.7. Then I put a little bit closer, 1.73. A little bit closer, 1.732. A little bit closer, a little bit closer, a little bit closer. I get infinitely close to this very specific thing I'm trying to calculate. Then what's going to happen is I'm going to then have a answer, which is approximately, because I can't ever really quite get there, of 3.321971 ... never ends. So all of this to tell you that the way that you actually calculate fractional exponents, like if you really had to do it by paper and pencil, I mean, we all know we can go to a calculator and punch it in there and get the thing. But what the calculator is doing is it takes successive approximations, really, really close, and to as many decimals as your display can show you, and it just gives you that guy, and it truncates the rest. It doesn't do it all the way, but mathematically, you can take this thing called a limit, which means we define a new function, which is called an exponential function, where the variable's up top in the exponent, and we let this variable get closer and closer and closer and closer to what we're really trying to calculate, 2 to the power of the square root of 3, and then we're going to get, however we get as close as we can to the real actual value. You can get a computer to calculate this thing to 100 million decimal places or 500 trillion decimal places. It's just going to take time. But mathematically, this thing called a limit is writing down what you're doing. You're getting closer and closer to calculate that value. This concept of a limit is the very first thing you learn in Calculus 1. It is really the foundation upon which all of calculus is based. So you've now learned it in general idea here in algebra. All right. So now that we know what a irrational exponent is, it's an exponent that has, it can't be written as a fraction. Mathematically, we would get closer and closer to the actual value by doing something like this. This is what a computer does. Calculus defines what these things are by taking this thing called a limit as the exponent of this thing called an exponential function gets closer and closer. Now what we need to do is solve a couple of problems to show you how to handle it if you actually have an irrational exponent there. So for instance, if you have 3 to the power of the square root of 2 multiplied by 3 to the power of square root of 2, how do you handle it? Obviously, I don't want to calculate all the decimal gory details of what that power is. I want to keep it exact. I want to keep it as a radical. But you follow the same rules of algebra to get there. So here you have 3 to a power, 3 to a power, the bases are the same, so you can add these exponents together. Square root of 2 plus the square root of 2. How do I know I can do that? I want you to think. This is exactly the same as x squared times x cubed. The bases are the same, I add the exponents. Bases are the same, add the exponents. But in this case, the exponents are just really weird. So what I have is when I add square root of 2 plus the square root of 2, it's just 2 times the square root of 2 because I've added them together. There's 2 of them there. Now I can leave this as the final answer. I can do that. But I want to go a little step further and try to simplify it if I can. I can write this as 3 squared raised to the square root of 2. How can I do that? Because I multiply, when I have a power raised to a power, I multiply them. That gives me what I have here. But I know that 3 squared is 9 to the raised to the power of the square root of 2. Okay? And that's the final answer. Now, do not try to, this does not mean that you're taking the square root of 9. It doesn't mean that the radical applies to the 9. It means that it's the number 9 raised to a power, but that power is not written as a fraction. It can't be, because this square root of 2 is irrational. If you put it in a calculator, you're going to get all these decimals that go on and on forever, because it cannot be written as 1/2 or 1/3 or 1/4 or 1/5 or 1/8 or whatever. It can't. It's just the square root of 2. That's the exact value. So you leave your answer as 9 raised to the power of this radical. Notice we used the same rules of algebra. We just added them together. Now, if you really had to calculate the decimal form of it, you would do something like this. You would start with a crude approximation, get closer, get closer, get closer, and you would get as many decimals as you needed to calculate, approximation for the answer. But the real answer would be this limit concept. You would take 9 to the power of x, and you would get x get closer and closer and closer to the square root of 2, getting more and more and more accuracy, and then in the infinite limit there, as you get closer and closer to it, that would be what the value actually is. All right, what if we have 4 raised to the power of the square root of 2, and then we're going to raise that entire thing, that's the square root of 2 there, to the 3rd power. How do we handle that? Well, it's the same rules of algebra. We have a power raised to a power. So we multiply those together. 4 times and then 3 times the square root of 2. Right? Now, of course, I can leave it like this, but I can simplify further, because you know that when you have 3 times the square root of 2, that basically you can flip the order of these guys here, right? So if I wanted to, I could say 4 to the 3rd power raised to the square root of 2. See, all I did was take these guys and flip them around, right? And I know that 4 to the 3rd power is 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64, raised to the power of the square root of 2. Of course, you could leave it like this, but this is simpler because I've reduced the exponent as far as it can go. The base comes out to be 64. These are exactly equivalent, but this is going to be a little bit simpler. All right, let's crank right along. What if we have 3 raised to the power of the square root of 2, and then we raise that whole thing to another power of the square root of 2. So this would be like, think 3 squared, and then I'll square that. It's just that the exponents are weird. They have these radicals in there. So it's still a power raised to a power. So I can multiply those powers together. So I can do it how, you can write it however you want, but I'm going to write this as 3 raised to the square root of 2 squared. Now this might look a little weird to you, but when I multiply the powers together, it's square root of 2 times the square root of 2. That means square root of 2 squared. All of this sits in the exponent of 3. Now the 2 will cancel with a radical because a square cancels with a square root. That's going to leave me with just a 2, what's left over. Basically, you can see that the 2 here will cancel with the radical, leaving a 2 behind, and 3 squared is 9. This is the final answer. All right, getting some practice here. Not too bad. Let's crank through the next one. What if we have 3 to the power of square root of 2 plus 2 over 3 to the power of square root of 2 minus 2. Now, notice that this plus and this minus, they all exist in the exponent. This plus 2 and this minus 2, that's all upstairs in the exponent. So a lot of students will look at something like that, stare at it, and just have no idea where to go. But remember, when you have things added together in an exponent, you can always write it as a multiplication. These are added together. So this is exactly the same thing as the square root of 2, and I'm going to multiply by another 3 squared. Why? Because the bases are the same. I can add the exponents together, and that's exactly what I have here. So I just break it apart and go backwards. On the bottom, it'll be the 3 to the square root of 2 times, you have a negative 2, 3 to the negative 2 power. All right? So let me kind of rewrite this here so I don't kind of destroy what I have. Square root of 2, 3 squared, and then I have 3 to the square root of 2, and then 3 to the negative 2. Now you see what I have. I have a situation where this entire number, whatever it comes out to be, is on the top of the fraction, but it's also on the bottom of the fraction, so they divide away. And so what I have is 3 squared over 3 to the negative 2. There's several ways you can do this, but I'm going to write this 3 squared as just 9. And then this is going to be 1 over 3 squared, which is all still in the bottom here. So it's going to be 9 over 1/9. That's what's down there. And so I can do the division here. This will be 9 over 1. That's what's in the numerator. Change the fraction, division, and multiplication. Take this and flip it over. It'll be 9 over 1. And it'll be 81. 9 times 9 is 81 over 1. So it's just 81. And that's the final answer. Now, of course, I could have just done it from here. I mean, there's multiple ways I can do it. I can subtract these exponents. If I want to, I could have gone, from this step right here. This is gone, so this would be 3 to the 2 minus a negative 2, because I can subtract the exponent. So that's going to be 3 to the 4th power. And when you do 3 to the 4th power, 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So you get exactly the same thing, whether you do it this way or if you kind of go the other way that I went. You're always going to get the same answer. All right, so same rules of algebra are always applying. All right, we have a couple more. What if we have, let's take a look at 7 to the power of the square root of 3 multiplied by 7 to the power of square root of 2. How do you handle that? Well, the bases are the same, but the exponents are different. So I can just add those. 7 to the square root of 3 plus the square root of 2. That all exists in the exponent. I can add them. This is like x squared times x to the 3rd. I can add the exponents. Now, a lot of students will try to do things with this. Well, they'll try to say, maybe this is the square root of 5, because they'll add the 3 and the 2. Or maybe they'll do something else weird. I mean, the truth is, sometimes there's just kind of a trick question, and this is one of those. There's nothing else you can do. You add the exponents, but you can't really add them, because what's underneath the radical is different. If you remember from radical rules, you can only really add them if they're like terms, and these are unlike terms. If it was the square root of 3 and the square root of 3, I could add them, but they're totally different, so you just have to leave it like this. So it's a weird expression, 7 to the power of this stuff, but that's what it is. All right, so let's change it a little bit from what I have above. Let's change it and make it 7 to the square root of 3, raise that whole thing to the square root of 2. So this is the square root of 3 on the bottom. Sorry about that. I can't really read that, so let me rewrite it. Square root of 3 on the bottom. And then you have a square root of 2. Here you have a power raised to a power, so you have the square root of 3 times square root of 2, because I'm multiplying the exponents together. Now you should remember back from radicals, when you have radicals multiplied, I can just multiply what's under the radicals. 7 to the power of 3 times 2 is 6, because when I have two radicals multiplied together, I can multiply what's under the radicals. So notice that when the radicals are added together, you can't really do anything further with it, but when they're multiplied together, I can multiply what's underneath, and that all comes back from the rules of radicals, the rules of fractional exponents. We've done all that in the past. Okay, so if you have any questions about why you're doing certain things here, you don't know why you can multiply these, that all comes from radical, the rules of radicals we've done in the past. So let's say you have 7 to the square root of 3 plus 2, that's in the exponent, and on the bottom here you have 49. How do we simplify this? Well, first of all, you notice 49 is pretty closely related to 7. So what I'm going to do is on the top, I'm going to write this as 7 times the square root of 3. These are multiplied, so I can added. So this can be times 7 squared. How can I do that? Because I can add these exponents together, which is exactly what I have. On the bottom, 49 can be written as 7 times 7, right? So what I have here is 7 to the square root of 3 times 7 squared over 7 squared. And so I can say, well, this 7 squared cancels with a 7 squared, and so what I will be left with is 7 to the power of square root of 3, and that's the final answer. So I hope you have learned from doing these problems that the rules that you apply to exponents when they're irrational are the same exact rules. Sometimes you can add the exponents, sometimes you can subtract them, you multiply them, you divide them. All the rules are the same. There's no difference in the rules, but you do have to get comfortable with the idea of having radicals running around. It's not just radicals. Pi is irrational. There are other numbers in math that are irrational that we'll learn about later that you can have in exponents. But it doesn't really matter. The main thing for you to understand is that anything you have in an exponent follows the rules of exponentiation that we've learned. Now, if you want to learn the details behind how a computer calculates those numbers on the screen, we kind of went through that. We talked about the concept of a limit, where in calculus you're going to learn that you can have a function. This is called an exponential function, where the variable itself, this is not like x squared. X squared is not an exponential function because this is just a variable raised to a number. This is different. This is a number raised to a power that is a variable. That's called an exponential function. We can use and make that exponent get closer and closer and closer to the desired value through this thing called a limit, and you get more and more decimals to get more and more accurate to your answer. That's a foundation of Calculus 1. All right, but for now, what you need to know is how to handle these things, how to handle these irrational exponents. We've done that here, and also to know that this is an exponential function. We're going to talk extensively about that, probably 6 or 7 or 8 lessons, and then we also have the concept of a logarithm, which is very closely related to an exponential function also. We're going to get there very soon. So follow me on to the next lesson. We're going to wrap up the concept of these irrational exponents in algebra.